That's what we get to see. Now I would like to recover this, but in the presence of noise is of course too much to ask. What I would like to do is I would like to recover this convolved with a filter, the same filter with a much narrower bandwidth. And this is really, I think, an interesting point of view because it says that this is a telescope I have, and this is a telescope I want. And the question is, how can you give me a signal at the resolution of the telescope I'd like to build? Okay? And so, of course, the object, if I want, I want to get an object, I would like to get the answer of the signal convolved with a much bigger telescope, which is this. And now, the problem that we're going to talk about is, you see this, how can you go to this when you have noise? Okay? In the limit, where this gets to 0, then of course we're back in this. But the thing that I care about at the moment is, this is what you have, this is what you want. Okay? And so, now we're going to introduce noise. And the super resolution factor, what we call the super resolution factor with Carlos, is a ratio between this and this. It's by how much you want to extrapolate the spectrum. So for example, if this is half of this, it's like I want to extrapolate the spectrum, I want to double the size of the spectrum. If this is 4, I want to quadruple it, and so on and so forth. Okay, so the same interpretation is here. It says, my telescope only lets me see the world in this narrow band, and I want to extrapolate the spectrum. I want to recover all this green side load because I want to extrapolate the spectrum onto here, and this ratio between this and this is the same quantity as what we call super resolution factor. Okay, so now what we've got is we've got a system in which we can have the same measurements, but now we've got noise. Now I'm going to take a noise model, which is quite simple. So what the noise model, what it's telling me is that, well, what the data I've got is a low-pass version of the signal X plus a noise term Z. So this is the low-pass version of X plus the noise term. Right? So I'm observing the low-pass version of X, which is essentially this, plus a noise process on top of it. Okay? And what I'm going to assume is that the noise is bounded in L1 by quantity times delta. Okay, so now I'm going to see, Pn of x, the low-pass version of the signal. This is a low-pass version, the version convolved with our low-pass kernel, plus the noise process. Well, and so I've got the true signal, and then I'm going to have the observed signal, which differs from this by, an amount such that, this average distance is delta. Okay, so I'm going to recover this by, again, convex programming, subject to, now I'm going to relax the constraint. I'm going to ask that the recovery is now within the noise level. Okay, so it's essentially the same strategy as before, but now with a relaxed constraints. Okay, and of course, if I do not look for super resolution factor, if I ask you to produce a signal at the resolution of your data, well, how well can you do? Well, it's just going to be the noise level of delta. But now, we're going to be ambitious and we're going to replace this with something which has a much finer scale. And so how is this going to degrade? Right? And so what we establish is that it degrades as the square of the super resolution factor. That is, as you're looking for a signal at a finer and finer scale, of course the error will increase, and it will increase as a square of the super resolution factor. So the higher the resolution, of course, the largest the error. Because when I have noise, all of a sudden I have an uncertainty about where these spikes are, and so as you ask me to locate them more and more precisely, this uncertainty will amplify. Okay, all right. So we've talked about super resolution signal by convex programming, and I think one of the things that we've not talked about is how would you run this on the computer? And I think this is kind of something interesting that at this, if you're practically oriented, you can be extremely worried about what I'm telling you now, because how on earth are you going to solve this problem? So think about it this way. It's like, really, this is kind of a very natural problem when we're asking. I have a measure, x. I get to see its first few moments, which are the first Fourier coefficients, and ask you, what is this measure? Right? That's really recovering a measure from a few moments. And this measure lives on the continuum, so this has infinitely, x is infinitely dimensional because it's something that lives over the continuum. So how am I going to discretize this? Okay, so I have an infinite dimensional variable x, and I have finitely many constraints. Now every program has a dual, and on the dual side, this optimization problem looks something like this. I want to maximize the real part of y dot c subject to fn star dot c in infinity is less than 1. Okay, so now when you look at this dual viewpoint, what you've got is now you have a new problem, a dual problem, which has a number of variables which is finite. In fact, the number of decision variables now c is finite. It's a number of points, of data points that you've collected. But now you have infinitely many constraints, because what does this constraint say? This constraint says that when you look at the trigonometric polynomial whose coefficients are the decision variable ck, you want this trigonometric polynomial to be less than 1 in magnitude. Okay. So now, when I look at the dual point of view, I have a finite number of variables, but infinitely many constraints. Now, the remarkable thing, and maybe some of you know this, because this is related to what people do in control. The remarkable thing is that the constraint that says that the trigonometric polynomial is less than 1 for all t 0, 1 is what we call semi-definite representative. That I can represent it as a semi-definite program. So who has never heard about a semi-definite program? And don't be shy. Okay, so it's semi-definite representation. I mean, this is an enormous topic in convex optimization, semi-definite programming. But so, what this constraint to say that a trigonometric polynomial is less than 1 is the same as saying that this matrix Q, C, C star 1 is positive semi-definite, which is an LMI, a linear matrix inequality that occurs in semi-definite programming. And so this is equivalent to this, that this matrix is positive semi-definite, the trace of Q is 1, and when I sum Q's along superdiagonals, they vanish. Alright. Okay, so this is semi-definite representable, so this program is actually a semi-definite program, and I can solve it. Okay, so the dual can be formulated as a semi-definite program. I can maximize the real part of y transpose c subject to, this is called the semi-definite, the trace is of Q is 1, and the sum of Q along superdiagonal vanishes. Okay, so I solve this semi-definite program, and now I get my C. Okay, so when I get my C, I'm going to retrieve the solution by complementary slackness, by looking at when this polynomial achieves the value 1, and this is exactly where the signal is non-zero. Okay, so what I do in practice is I solve the semi-definite program, and I check my trigonometric polynomial, and I see when does it reach magnitude 1, and this gives me the support of the signal. So let me show you some numerical experiments. Here is an experiment. So here I've got a real measure, I have a real signal, and here you see the sign of the signal in red, and in blue I see the trigonometric polynomial as found by the semi-definite programming solver. And what you see is that when the trigonometric polynomial reaches a value plus or minus 1, it actually exactly corresponds to a location where the signal is not zero. Okay? All right. then look at those values, and we recover the support of the signal, and that numerically, what is our accuracy? Numerically, the accuracy is like just the accuracy of your solver. And so when I use an off-the-shelf solver, I get to see that I recover the location of the spikes with 10 to the minus 10 accuracy or something by solving this semi-definite problem. Okay, so here's an example. An example is you see this blue curve that looks like this. I solve the semi-definite program, and the truth is this red dot, the black is my recovery, and so you see that I'm completely spot. Okay, so now we have, like, computationally, it seems, at least the computational tools to actually locate these things very precisely, and that what we require is to solve a semi-definite program, a special form of convex program. Okay. All right, so I mentioned at the beginning that I'm working with a chemist at Stanford to do single molecule imaging, and so we have begun a collaboration with also my postdoc, Emmanuel from Stanford, and so we're applying all these techniques to enhance the resolution of microscopes. And so this is the kind of application I was talking about before, where we've got these molecules, and these molecules will appear to be extremely blurry under the microscope, and we need to locate them very precisely to know where they are in the synapses. Okay, so maybe I should turn off the lights, or maybe the movie again. Okay, so you see that these molecules, this is a true state of nature. These molecules are right here, they're very tiny, and under the microscope they would appear as completely blurry like this. And in fact, they don't appear like this if you have noise on top of it, because you have this kind of Poisson noise. Everything in optics is subject to Poisson noise in fluorescence microscopy. And so you get to see a low pass plus noisy version of this. Right? So a model that people use, or that we use, is that, well, the data collection will be, well, you're going to have a Poisson random variable, which models the fluorescence, which is a low-pass version of X plus an offset that has to do with the fact that you're collecting light that you do not want. But you have a background. You have more than these molecules. You have a fluorescent background. And so you've got many problems to deal with simultaneously. You've got the problem we've talked about, which is you have low-pass data. You have the fact that you have a background which is not really known, and you have the fact that you have noise, which is Poisson distributed. All right. So now what we're going to do is we're going to use the program we've talked about, except that now you're going to adapt it to deal with Poisson noise. So you're going to do maximum likelihood estimation. So this is the likelihood of Poisson data, and you're going to regularize it by this TV norm that we just talked about. And so when you look at your original signal and you run this optimization thing, it's going to actually locate these molecules quite precisely. All right, so what we're doing is we're doing that with, thanks to the work of Merner and his colleagues, we're doing something which is quite ambitious, which is actually going to do 3D localization from 2D samples, from 2D data. So this chemistry group at Stanford has a very nice trick, which I can explain offline if you want, to try to infer depth from phase. All right, so so what we're trying to do is, so in a very short amount of time, all I can see is that the point spread function that they get is z dependent. Right, so by looking at the point spread function, you can tell what the depth of a molecule is. So they collect 2D images, but because the point spread function is z dependent, you can actually recover depth. Okay. All right. And so what we've got is that's what Merner's microscope collects. It collects a lot of molecules which are blurred, which have a point spread function whose orientation depends on z. They all collapse onto each other. And what we would like to know is we would like to recover the locations of this molecule in x, y, z space with as much accuracy as possible. Okay. And so this is what we can get. We can go from data that looks like this to data that looks like this, and then we can lift this up to recover x, y, z. So when you look at the performance of this algorithm, this TV minimization algorithm, it performs much better than kind of the state of the art in microscopy. And so why is it that my colleagues at Stanford are excited about this? It's because they want to image as many molecules as possible, simultaneously. Right now, what the algorithm does is when two molecules are too close to each other, the algorithm just refuses to work and it just throws this data away. And so they can only image molecules that are very far apart. This method could not care less about distances. It can do anything because all it does is just solve this. And so with this method, we can increase density, we can increase the number of molecules per frame and still maintain high accuracy. Okay, and so for biology experiments, this is, from what I hear, quite significant. And so it's just work in progress, and we're working a lot on this. And so the preliminary results we see are promising, and so they're excited because maybe we can increase density and make experiments much faster than they're used to. Okay. Yes?
Now there you mentioned that your colleague in Stanford doesn't care less about distance between the molecules. However, there you mentioned that the signal shouldn't be too close.
Of course, of course.
So what's the seems that
of course. So the algorithm does not care. See, I can run this algorithm no matter what I see. What the theory says is that if the molecules are close, I may not be able to do a good job. But to run the algorithm, I don't need to know anything. Okay? Now, you look at the result and you see points that are clustered, you'd say, aha, maybe let's not focus on this. But the algorithm is completely agnostic. Now, their algorithm is quite different, and maybe when the light will come back up, I'll explain to you why they cannot deal with high density. I'll tell you what the algorithm does, but before I do this, I want to finish that in reality you have a background that looks